Hey, good afternoon. So welcome. Again, I acknowledge the support of the Atkinson Center and Biological Environmental Engineering Department. So I'm really happy today to welcome Stephen Davis. So Stephen is a professor at University of California at Irvine, and he pursued a rather unusual pathway to where he is now. He got his Bachelor of Arts in Political Science and Philosophy at University of Miami. And then he went on to get a law degree at University of Virginia. And then he became a corporate lawyer. After that, he decided to go back at PhD in Geological Environmental Sciences at Stanford. And then he joined the faculty at in Irvine in California. And so Stephen studies how to satisfy the global demand for energy, food, and goods without adding CO2 to the atmosphere in a sustainable manner. He received the prestigious Macklin Award from the American Geophysical Union for his contributions for developing a science that links global climate change and society. And so let's welcome Stephen. It's our long trip from California, and we're very glad you made it.
Thanks a lot for that kind introduction. Appreciate that, Peter. And it's really fantastic to be here in person with you all. I've had some great meetings today, and it's the first I've traveled for work in like 2.5 years. So it's glad for me that it can be with you. So as you see from my title today, I'm going to kind of break this into 3 chunks. I've been watching a lot of This American Life. I don't know if anyone likes that radio program, but they always have acts. And so I was inspired to make this in 3 acts or parts. So there'll be one on energy, one on land, and then one on carbon removal. And all of these really are in the theme of how do we solve climate change? How do we stop adding CO2 to the atmosphere? So just to give you some background before I get into the different parts, hopefully you've got some sense that we have these global climate targets now. We want to avoid a certain amount of warming relative to the pre-industrial era. And the most ambitious of these is to try to avoid 1.5 degrees of warming. So this plot shows what global CO2 emissions would need to do under a bunch of different scenarios. So this is from an IPCC report in order to avoid that 1.5 degrees of warming. And so what you see is that they reach this horizontal red line is 0 around 2050. So the numbers are a little bit small, but that's 2050 there in the middle of the plot. And then in many cases, you have many gigatons of negative global CO2 emissions after that point in time, as we try to remove CO2 from the atmosphere to stabilize at this lower temperature. So this happens, net zero happens around 2050 in the 1.5 degree scenarios. In the 2 degree scenarios, which was sort of the previous target, it happens a little later. I'll show you that in a second. So if we dig into some of these scenarios, now I don't know if you guys have heard about integrated assessment model scenarios, or ones where we have some idea of how population and economies are going to grow. And we know something about how much different energy technologies cost. And we say, we want to hit this climate goal. What's the best way to do that? So different models are set up differently. But if we look at all of these scenarios that manage to get to different goals, there's 177 on these plots. The left side shows for different temperature targets in different colors, the relationship of per capita GDP, or more or less income, and final energy use in these different scenarios in the year that they hit net zero. So this is the place where we're not adding any new CO2 to the atmosphere. We've reached this net zero, but you can see from the colors, these are different actual targets. So the blue ones are the 1.5 degree, and you can sort of see by the distribution that they tend to have less energy and per capita GDP. Now you might think that's sort of funny because they're more ambitious. Why does it mean that we're hurting our economy to get to those goals? No, that's not really what's going on. In fact, it's just that they happen earlier. So we expect the global economy to grow at a certain rate over time. So if you're going to hit a target later in time, then you're going to be richer when you get to that target. So that's what's happening. And it's kind of evident in the right side plot, which is on the x-axis is showing you the year that these scenarios get to net zero. You see the 1.5 degree, as I told you, is more like 2050. versus the year peak emissions on the vertical axis. And you can see that given that dashed line is the present, we needed to hit peak emissions yesterday for a lot of these scenarios. So this is sort of what we're up against. And if we look at what actually is being used for energy in these scenarios, this plot is showing you how much on the x-axis of our primary energy is from renewables versus on the y-axis, how much of those renewables are non-biomass renewables versus biomass. So towards the top, you're using more solar, wind, and hydropower. Toward the bottom, the scenarios are calling for more biomass to get to net zero. What you can see, though, is all the colors are sort of mixed up in this shotgun blast, telling you that the models are all over the place with respect to how we're going to get to this point. There are just as many that are saying we're going to use more biomass as there are saying we're going to use more wind. Now, these are global models that don't resolve in a lot of detail, like the hourly demand and supply of electricity. So we shouldn't put a whole lot of stock in those. But you can see that 60% of the energy in most of these cases are coming from renewables, meaning that we still, in a lot of these models at least, are using fossil fuels. So if I plot on this triangle, the share of the energy that's coming from three sources, either nuclear, fossil fuels, or any renewables, what we see is that there's relatively small amounts of nuclear being called for in any of these global models. And there's a real trade-off between how much renewables and fossil fuels are still getting used. Now, if you're not an energy person, you may be thinking, how in the world are we at net zero for using a lot of fossil fuels? That doesn't make sense. Well, it's because the models are using a lot of carbon capture and storage, which is not really something that's very popular and probably not something that's entirely necessary, but it's something these models still deploy a lot of. The last one before I dive into the meat of my presentation, sorry about the Zoom commands there. What I'm saying there is that there's a lot of differences among these scenarios in how much bioenergy with carbon capture and storage the models call for, how much renewables growth are being called for, and how much of what we call decoupling, the separation of economic growth from energy use. And so what we can see here on the x-axis is how much of this decoupling is going on versus on the vertical axis, how much annual increase in renewable energy we need. And this red square that I've added shows sort of what we've been doing historically in the last few years. So what you can see in the 1.5 degree dots is we have sort of this stripe of those that go up and to the right that suggest really rapid growth in renewables going forward. And then another set that's not growing as quickly on the renewables front, but sort of shows a decoupling of our economy from our energy use. Okay, so this is all just by way of background of what are we up against? What are the global models saying? And I want to first, in Act 1 of our program today, talk about energy CO2 emissions. So the good news, and hopefully this is something that you've all heard, is that there are some pretty clear pathways to what I'd call deep decarbonization of our energy system, ways to make big decreases in our emissions. And these have really emerged as clear frontrunners just in the last 5 to 10 years. But it shouldn't probably surprise you that things like solar and wind have come down in price. They're going to be taking up a lot of the energy mix in the future, we hope. And as far as end-use technologies, we're going to try to increasingly electrify those things. So we're going to use electric vehicles, we're going to use heat pumps so that we're getting our electricity from non-emitting sources, and then we're using that electricity for more and more things. I would say this tells us we've got decades of work to do just with the technologies that you see here to help drive down our emissions to really low levels. But my group's done some work to explore the parts of our energy system that are more difficult. So what are the more challenging things? Well, probably you've thought about how do you fly an airplane? It's one thing to maybe have a short distance airplane or a really small one that might even be electrified with batteries like cars. But if you want to fly on a jumbo jet across the Pacific Ocean, you're not going to be able to do that with batteries. What else? Well, cement and steel are solvable but challenging. So getting these things without emitting CO2, turns out you may have to actually change the process of how you're producing those materials. And the one that I'm going to focus on more today is how do we make sure that our electricity system remains reliable if we're going to be basing it on these variable resources like solar and wind? What are the challenges there? So how much of these difficult pieces are going on? This pie chart shows all of the fossil and industry emissions in 2014, a little out of date, but it hasn't changed much. And the pieces that are sticking out further here are the difficult pieces that I just told you about. We've got our iron and steel there in blue and cement in purple, and the difficult to decarbonize parts of the transportation system in orange. But it's this big red wedge that we call the load following electricity that I would argue is a little more difficult. So we have to have some way of backing us up when the sun isn't shining and the wind isn't blowing. So if you look at a different set of models that does resolve more detailed intricacies of the power system and what the dynamics are with solar and wind availability, you start to see that a lot of these are really relying on a lot of solar and wind in the future. So these circles in purple and yellow are systems that are modeling just the US and Canada or just the EU. And you can see that the solar and wind share of all the power is upwards of 65, 80% in some of these. So that's something that's interesting. And I put this up just because it had a lot of different models all on one plot, but many, many models have come to this conclusion that we can get about 80% of our electricity from solar and wind. And it's remarkable that different models that are set up in different ways have all sort of reached this conclusion that we can get 80% of the way to a decarbonized electricity system with solar and wind. But even when we're trying really hard, it seems hard to get past that threshold. And so something that my group was interested in is, to what extent is that 80% rule of thumb somehow dictated by the geophysical variability of solar and wind energy? How much is it that's just the character of the resource that we can't get further? And so we did an analysis that looked at this in a somewhat stylized way. So we made these very simplifying assumptions that said, what if we could connect the entire area of the United States with a power grid such that, you know, sunshine hitting a solar panel in Connecticut could instantly be used in California? So obviously that's not how it works. We don't necessarily have those power lines, and there'd be inefficiencies to shunt power across those distances. But we wanted to look at just what's available. And so this is showing you the average amount of solar and wind that the United States gets, the continental United States, over a given year. So the yellow is solar. And what you should see is hopefully logical to you, that we get more sun during the summertime and less during the winter. What may not be as intuitive to you if you haven't paid attention is the wind, which is in purple here. And you can see it's sort of the opposite. We tend to have more wind in the wintertime and less during the summertime. The other thing, though, is the shading, right? You can see that there is a little bit of shading, if you can make it out, around this yellow line. There is some variability, a cloudy day or not a cloudy day. That should make some sense. But the variability in the wind is a lot bigger. So this is weather data over the US, I said, averaged over a period of 36 years. And that variability tells you that it's going to be possible to do a lot of offsetting of solar when they complement each other, but that variability tells you that it may not always be possible to do that. In contrast, this orange line is our average demand, which tends to be summer dominant right now. That may change as we electrify more things. So as I mentioned, we built this model that said, okay, let's assume we're trying to get as much of our electricity as possible from solar and wind. We're going to use the resources in the US to do this. How much of the time could we meet our demands with just solar and wind? So we're not saying we're going to do without the rest of the time. It's just that that's going to have to be filled by some other resource. So what you're looking at here, and there's going to be 4 of these, is a plot that shows how many hours of the year of demand are being met by a different mix of all solar at the top of that or all wind at the bottom of that, and mixes in between. And as you move from left to right in this panel, you're expanding over a bigger area. So what we're getting at here really is that if you want to get a lot of electricity from solar, it helps to spread out your solar panels, right? A cloud might pass over Ithaca, but it's not going to pass over Ithaca and Arizona at the same time. So if you spread those things out, you're going to be more reliable. So as you go to the right here, you see you're meeting more of the hours of demand. And in this case, we've assumed there's no ability to store energy. And the amount of solar and wind that you've deployed is such that over the course of 1 year, you get exactly the amount of electricity that you need for the year, just not necessarily in the same hour as you need it. So that's the 1x generation. What else could we do? Well, we could add the ability to store some power. So in this case, we've now added the ability to store up to 12 hours of average demand in the US. And you can see all of a sudden that you're now in a situation where you're no longer a wind dominated. Because you can overcome the diurnal cycle, you'd like to have more solar. You also can notice here that you're crossing a lot fewer contour lines as you move laterally across these panels. Now that sort of suggests that once you have the ability to store 12 hours of electricity, then it doesn't necessarily advantage you to spread out so much. You can concentrate your panels in a smaller area where the solar resources are good and use your storage to back you up. I think this is really important though, because it sort of suggests that we in the US have sort of two options. We can really concentrate on building out a transmission grid that can move power around and build a lot of wind, or we can dominate our system with solar and build a lot of storage. And it may not be beneficial to try to do both at the same time. Now, the bottom ones here are just going to show you the same type thing, but in this case, instead of exactly the amount of electricity in a year, you're going to get 150% of the electricity you need in that year. So you're overbuilding, knowing that you might have to throw away some power or you might have to use it for something else, but you'll have more hours of your demand met. And so the numbers get a little brighter. And in the case where you've got 12 hours of storage and you've overbuilt your system, you're finally getting to the point here of maybe getting to 99% of your demand being met. Now, I should say here that 12 hours of storage sounds very reasonable, right? 12 hours doesn't seem like that long, but it really matters how we're storing that power. Right now, we have far less than that available to us, and most of it is in reservoirs that we pump water uphill and let it back down when we need it. If you wanted to build batteries for 12 hours of storage, it'd be about 125 years of the Tesla Gigafactory's output. So 12 hours is an awful lot of batteries. So we should be a little bit nervous about needing 12 hours if we can not have to have it. So really what these figures are showing you as you move from the left panels to the right is the benefits of that storage. Within each panel, we're getting at the benefits of building a transmission grid that does well across the US. And then in the top row versus the bottom is the benefits of overbuilding our system. So I should say also, we overbuild our fossil system. We have more capacity than we need most of the time. So the idea of overbuilding is not necessarily just something about renewables. So this now is showing us in the same system where we have got 1 times generation and no storage, we're only 62% of the hours. And if I put all the 36 years of data there, you can see I pull out 1 week in December of 2014, I think it is, what's happening during that week. So the top of that shaded area is what demand was in that week. And you see the yellow of solar is coming in and out every day. But demand is not being met by the purple of wind. Wind is basically not able to meet demand. So we have this cross red area of unmet demand. Now, if we look at the same system, but now we've got 1.5 times generation and we have our 12 hours of storage, we're 99% of the hours looking good. But this same week, now you see there's still 5 days in a row where a substantial fraction of demand is not being met. So the point here is, even when we get to 99% reliability, that's actually far less than we need and actually by law require our power systems to be. So resource adequacy in the United States, the legal requirements are 99.997% reliability. So it's only like a few hours of planned outages for a decade. So we actually would not be happy with that. But my point really is that even when we've overbuilt and we've got this storage, we still have some gaps here that are going to be tough to meet with just solar and wind. So we need something to back us up. So we've now done this not just for the US, but looked at other countries around the world. And as you might expect, larger countries have more reliable systems because they can integrate over that larger area. Countries at higher latitudes tend to be worse in terms of solar, maybe better in terms of wind. So we've kind of looked at what happens in different places around the world. Really, we find though that in the case where you've got no storage, you can often get into the 70, maybe 80% reliability or higher, dominated by wind. Where you do have storage, you can be above 80%, maybe up into 90% in this really simplified model. And that gets, of course, better as you overbuild. Now, one interesting thing we were able to do with this study is look at what's the advantage of overbuilding. And we found like every 10% of excess generation you have is equivalent to about 4 hours of energy storage. So that's a useful rule of thumb, because if you're thinking about, wow, batteries are really expensive, but so are power lines, and how should we think about trading these off, or rather extra generators, you can sort of do the math to see what might work out. And really, no matter where you look, there's different gaps. So these curves are showing you for how many hours out of the year and how much of demand are you going to still need under different solar and wind systems only. And really what we find is most cases, you might need somewhere from 25 to 50% of your demand met for 100 to 300 hours a year. So all of this is meant to give you the idea that we can get a long way with solar and wind, but there's still this like really difficult bit that you need something else. You need some storage, certainly helps, or maybe you need what we call firm generation capacity. Something like hydro. You guys have a lot of hydro here in the state. I was talking to Professor Howarth earlier about this. That's something that if you can be flexible and turn it on when the sun sets and the wind's not blowing, you can back yourself up and ensure that reliability. But what you'd really like, given that the gaps can be multiple days and a large fraction of demand, that's a lot, right? You have to have a substantial capacity, but it's very rare. It's only a few hundred hours per year. This is like if you want to think about what's the cheapest way for you to pay for transportation if you need to drive to Syracuse once a year, it's probably not to go buy a Ferrari, right? Because that's going to sit in your driveway for the other 364 days and do nothing for you, only take your check, right? So you're going to want to buy something that is necessarily low in capital costs, but it could be high in variable costs because you're not using it very often. So this plot shows you the different types of energy on the vertical axis being the fixed capital cost versus the variable cost. So how much do you have to pay when you're operating it is on the horizontal versus how much you have to pay no matter how much you operate it on the vertical axis. And you can see that the things that are really cheap in terms of their capital costs tend to be things like natural gas combustion cycle turbines or any kind of natural gas, really. But what, of course, we want is that economic flavor of low capital costs without the CO2 emissions. And so that's the kind of firm generation we're looking for. And if we look at storage technologies, what you see here on the horizontal axis is a different metric of how often are we using this, cycling this storage thing every day of the year versus once a year. And you can see, kind of like my Ferrari example, the less often you're using the storage technology, the more you're going to be paying for every unit of electricity that you discharge from it because you're paying the capital cost for it the year round. Anyhow, all of these things then curve up, but you can see that even if we're successful at meeting our fairly ambitious targets for how cheap lithium-ion batteries will be in the future, they still are very expensive if you're only cycling them maybe 20 times a year. Something that is potentially attractive is if we can figure out how to generate green hydrogen for on the order of the current price of hydrogen, $1.50 a kilogram, we can store the gas much more easily than we can store electricity, and this can be our storage. So the reason that's especially attractive is that you can buy a really small electrolyzer and let it operate for most of the year. So it's constantly operating, but you don't have to buy a big one. When you buy a battery, the costs are dominated by how big the battery's energy capacity is. And since we need a lot of energy, then it becomes really expensive. In the case of hydrogen, it's really, you can buy a tank or put it underground pretty cheaply. So it's more about the cost of the electrolyzer itself. And if you can get one of those that's sufficiently small, you can run it the year round. And we've put this in a model of the energy system where we've allowed the model to only have solar, wind, batteries, and hydrogen storage. And what you see is the battery tends to cycle very frequently. Day to day, it's helping to balance the differences between supply and demand of the renewables. On the top, though, you see what happens with hydrogen. It basically builds up really slowly for most of the year. And then in the times when we most need it, when the sun is starting to dip there in the fall and the wind has not yet come up, we have these big gaps and you draw down all of that. And so it's a different mode of storage. And in this particular model, we see that even at the current pretty high costs of hydrogen electrolysis, it already helps these solar and wind-based systems to be cheaper. So the takeaways from this first part of the talk about energy is that, our analysis suggests the geophysical variability in solar and wind resources really do kind of define how much of these backup, whether storage or flexible generation, you're going to need to have a reliable system. And the character of these gaps is that they're big but infrequent, which really hurts in terms of the economics. You need something with low capital costs. And finally, that our economic analyses suggest that some of the benefits of long duration storage are going to be accruing where we can have technologies that have low power capacity costs, and like hydrogen power to gas power. All right, so moving on to Act 2. Hopefully there's a flavor for everyone in the room here. We're going to talk about land use greenhouse gas emissions now. So just to bring you up to speed, if you're not already there, there's really two main buckets of land use emissions. There's land use change, which is the deforestation everyone hears about, where we're changing between unmanaged land to managed land, like cropland or pasture, or changing between those or harvesting timber. And then there are agricultural activities, things like the nitrous oxide that comes from putting fertilizer on, or the fermentation in the guts of ruminant animals. And so the first of these we try to keep track of using what are called bookkeeping models. So we know how much carbon on average is stored in a tropical forest in a given region. And we know if you tear down that forest and shift it to cropland, how much CO2 will emanate from that. On the other hand, we also have some idea of how much emissions are coming from these other different processes. It's something that's tracked pretty well by the Food Agriculture Organization of the United Nations. For example, about 1% of the nitrogen that you apply to a field is ultimately volatilized as the greenhouse gas nitrous oxide. So what my group did was to actually try to assign these emissions for the last 50 years to specific products and places. And so first off, I should say we found that the total of these land use emissions in recent years is about 14.5 gigatons of CO2 equivalent emissions. And this is using a global warming potential of 100. We looked at a bunch of different ones, but that's what was plotted here. Now, just to tell you, that means that the land use change and agricultural emissions are about a quarter of all anthropogenic greenhouse gas emissions in recent years. And I think despite that, they don't necessarily get enough attention. So that black line is the net. The stuff on the bottom here is actually associated with places where we've abandoned agricultural land and we're seeing regrowth of natural landscapes. And really the other interesting thing is that dashed line shows that the fit has a kink in it. Around 2001, we see it starts to increase, and it's been going up by almost a quarter of a gigaton of CO2 equivalents every year since 2001. The other thing here is it's breaking it down by regions, and you see about 55% of the net cumulative emissions are represented just by Latin America, Sub-Saharan Africa, and Southeast Asia, places where our land use change is happening a lot. So we can also look by different processes that are creating this, and just to say that really conversion to cropland and enteric fermentation that I mentioned in ruminant animals represents a lot of the net emissions, something like 96% over this period. Again, there's some uptake here by agricultural abandonment. So then the more exciting stuff to me, because no one had done this to the same extent, was to actually assign these emissions to specific products. And these are actually aggregated groups of all the products that we figured out. In our base case accounting, we assign the land use change according to the area of different crops that were getting grown or livestock. And we're doing that in the paper in these figures. We also did a bunch of other alternative assumptions where you assign it by mass or by the amount of calories produced using different techniques just to sort of test the sensitivity. Something important to mention is this is not assigning emissions from a crop that was fed to an animal to the animal. We're doing it on a what we call production-based basis. So everything is assigned to the crop that's initially grown. And you can see that the cereals, beef, and oil crops, as well as the dairy there in the lighter blue, are 90% of the total net. And finally, just to show, a lot of this is CO2, but there's a big chunk of it that's methane and some more that's nitrous oxide. Okay, so further to this work, I don't know if anyone in here knows the Kaya identity. This is a way that we study fossil fuel emissions and try to understand how these fossil fuel emissions are changing with energy and what kind of energy we're using, how efficient and so forth. We came up with a variant of that for this paper called the Pale identity. And this is it. Really, it's land use emissions is E, showing it as a function of population, how much stuff we're growing per person, how much land we're requiring to grow that stuff, and how much emissions are coming from every unit of land. Now, the reason I like to break it down like this is because each of these terms is another sort of lever about how we could reduce these emissions going forward. In theory, we could control population. That's not going to probably be the way to do this, but we definitely could change how much stuff we're growing per person, or we could get more efficient with that. We could waste less, we could change diets, right? On the land intensity of agricultural production, that's something we've been doing pretty well at. We can increase our yields, right? Get the same amount of crops or more from the same area of land. And the last term here, emissions intensity of land, we could actually change the practices of how we're using the land. So if we look at how these things have trended over time here, we have three samples. The left one is the global analysis of those terms. The middle one is Southeast Asia, and the right one's North America. The bottom plots, maybe focus on first, show the balance between land use change and agricultural emissions, those two buckets I mentioned at the outset. And in recent years, globally, they're roughly half and half. But you can look across here and see that Southeast Asia is very much dominated by the land use change, whereas in North America, land use change emissions, although it's a bit jagged in recent years, are near zero. So it's almost all agricultural emissions. This already starts to tell you that we have some pretty different approaches to reducing these emissions depending where you are in the world. The other thing to note here, oh yeah, I guess that's it. So the other thing I guess I wanted to point out, if you look at the global plot here, population's been growing, so that's going to tend to pull up land use emissions. The same with the purple line is how much stuff per person are we cultivating, and that's been going up. That has to do with, for example, as people eat higher on the food chain, they eat more meat, then we're going to have to grow more to feed an animal that is inefficient when we then eat the animal. So that's part of what's going on. But more or less, those have been offset by, you can see down in the bottom, it's the blue line, the land that we're requiring to produce a given amount of agricultural commodities has been decreasing over time. So we've been getting better and better at producing stuff from the area of land. And so those are sort of balancing, and really the jaggedness in the black line of emissions is mostly to do with changes in the emissions of the land that we're using year to year, which often leads to, or really is driven by what is going on with land use change from year to year. So one plot that I really like to look at is this one. It shows in contours how many tons of CO2 equivalent greenhouse gases have been produced per person in these different regions as a function of how many tons of CO2 equivalent emissions are we producing per kilocalorie, per million kilocalorie produced. And on the vertical axis, how many of these kilocalories are being produced per person. So as you go up, you're producing more stuff. And as you go to the right, you're emitting more to make the same stuff. You can see in the black bold line, the global trend is actually decreasing the emissions intensity of our production, but it's not necessarily increasing drastically in the amount of stuff we're producing globally. The other thing to notice, this dashed line is showing you half a ton of CO2 equivalent per person. And you'll see that nowhere in the world are we emitting less than half a ton of CO2 equivalent greenhouse gases per person per year. Now that's a problem, because if this is some kind of frontier and we're never going to be able to get less than that, and we're going to have 10 billion people on the planet, that means land use emissions are necessarily going to be 5 gigatons of CO2 equivalents per year. And that's not conducive to getting to net zero. So if we want to get that net zero goal, we have to figure out how to break through that threshold and do better. So we have a table here that shows, what fraction of all anthropogenic emissions are associated with these land uses for different products. You can see, like I mentioned, it's about a quarter in total. Beef is a huge one, right? Something like 5% of all anthropogenic emissions are related to beef. And it turns out it's much less than 1% of calories that we consume. But it's important for everyone to realize not all meat is the same. Chicken is actually relatively low in terms of the amount of greenhouse gas emissions. It's 0.1% of all human emissions. In contrast, spices, which includes things like coffee and tea, is almost 1. So almost an order of magnitude higher. And no one's really complaining about cinnamon, Oil crops is another huge one. So this is something I'll mention in a minute, but oil palm in particular and soybeans in the Amazon. So we've got all these data. We put them up on a website. If you're interested, you can go and check, look at your favorite countries and products and processes. So more recently, we've actually fed all this data into a model of international trade, because people are interested when they hear there's deforestation happening in the Amazon. They want to understand, well, how much of that is consumption in places like the US? So when we did this analysis, what we find is that indeed, Brazil is a huge net exporter of emissions. So a lot of the emissions that are happening from land use in Brazil and Indonesia are actually going to be supporting consumption in other countries like the US and Europe and increasingly China. So this map that I'm showing you is from 2004, the state of affairs. And you can see a little more than a quarter of all the land use emissions in that year were being consumed in a different country than they were produced in. What's interesting, though, is if we look at the changes over time, which is all these maps, you can kind of see in the big arrow that was in 2004 from Brazil to Europe kind of diminishes by the time you get to 2011. Sorry, these controls are blocking it, but that arrow at the top, 129 up in Europe, is a lot smaller. And really, it's increasingly going to China. And that just has gotten stronger. So the most recent year of data in 2017 shows that now a huge amount of the land use emissions from Brazil are being exported to China. And a lot of this is soybeans that are going to China to feed livestock in some cases. So as I said, a big part of the increase over time in the total has been in these oil crops like oil palm and soybeans. But cereals are also a big part of it. And if we look at kind of a breakdown of the biggest traders, we see, as I mentioned, huge imports of soybean to China, and this is in 2017, and then big exports of soy and cereals from Brazil, as well as especially from Indonesia, a lot of oil palm being exported. And this kind of breakdown, being able to attribute these emissions to specific products and then look at where they're going, is a big benefit as we get more and more serious about decreasing these emissions. So as I mentioned, about a quarter of all human emissions from these land use processes. I think some people don't necessarily realize that that's a big part of the pie to getting to near zero, or net zero rather, and that nowhere in the world is less than half a ton of CO2 equivalents per person per year, and a big part are being traded. All right, so part 3, the last of the 3 for today, I'm going to talk about something that my group's been looking at for removing carbon from the atmosphere. So remember, I mentioned in that very early slide that a lot of the scenarios to avoid 1.5 degrees of warming actually get to where we're on net every year removing carbon from the atmosphere. Something that people are interested in is whether we could artificially grow a lot of seaweed to help with this problem. Now, how would that work? Well, as a seaweed is growing, it's taking up carbon just like any plant and storing that in its tissues. And eventually the idea is that you bundle up that seaweed and sink it to the deep ocean as fast as possible, where it would be sequestered for some number of years. We are interested in at least a century keeping it out of the atmosphere. Now, some of the questions then are, how much of that carbon that's sunk to the bottom of the ocean is compensated by an air to sea flux of carbon? That's the whole idea, after all, right? To reduce the CO2 in the atmosphere. And a lot of it has to do with biogeochemistry of what's going on downstream. So these seaweed farms are taking up carbon, but they're also taking up nutrients from the water column. And the question then is that just preventing something else that would have grown downstream from growing, such that you might not be doing anything really valuable? So our group has built a model to look at this globally, trying to estimate for different types of seaweed, how much could you grow in different places in the ocean? The first step in doing that was to look at the biophysical processes. So this is showing some of those. We have some nutrient constraints. Our model is constrained by nitrogen only, but there are micronutrients and phosphorus to think about. There's light. You don't get as much light at the higher latitudes, certainly sometimes a year. Temperature can dictate how quickly the seaweed's growing. And you can see some of the variables that go into this. In particular, it turns out, I'll show you in a minute, things like how much of the seaweed is sort of dying and sloughing off as the plant grows over time is something that's pretty uncertain. So we came up with 2 scenarios for the nutrients. Some of the early work that did this just looked at, okay, there's X amount of nutrients in this water. Let's assume it's all available for seaweed to grow. And they made gigantic assumptions about what could be done. But that doesn't really factor in any kind of sustainability, right? You may only get that harvest for 1 year, and you're certainly going to have an effect on the other things in that ecosystem that need those nutrients. So we have another scenario on the right that's what we call flux limited. So we used a global climate model to look at how much nutrient fluxes up from the deep ocean into these different areas. And we limited our seaweed to only use those fluxes. So it should be more sustainable. And certainly it's a less amount of nutrients. You can see that some of the patterns here. So this model is resolving at 1/12 of the degree, something like 10 kilometers at the equator. So there's some fine scale details you can't make out, but you can see those yellow and greenish areas are where you might be able to get quite a bit of carbon into the seaweed at least. As far as what kinds of seaweed, we looked at 4 different major types. It turns out the brown, there's temperate browns, things like Saccharina and Macrocystis. And then tropical reds are in the bright red, and that's things like Eucheuma and Gracilaria. So those sort of dominated. Am I doing okay in time?
Good.
Okay. So because we don't really know a lot about how seaweed does in the open ocean, most of the seaweed that's grown today, and there's quite a bit, it's grown very close to shore in places that are pretty nutrient rich because they have a lot of runoff from anthropogenic activities. If we were going to try to do this in a big way for carbon storage, though, we would need to take up space out in the open ocean. And that's sort of really open to discussion because we haven't necessarily explored it. We don't know how seaweed would do out there. So when we did that, we varied all of those variables over large spans because we don't know some of the details of how it would grow. And we found that, some of these terms, as I mentioned, the exudation rate and the mortality rate of those seaweeds, which is not well known, tend to make a big difference in how much you would actually get. So once we knew sort of something about how much seaweed we could grow, we started to think about, well, what would it cost and how valuable would it be? So for that part of the analysis, we started thinking about, capital costs. You need lines and anchors and boats and buoys. How much do those cost? how much do they need reinforcing in wavier places, or you need longer lines and heavier anchors in deeper places? How far is it to a port? It costs money to travel in a boat, especially if you're hauling a bunch of seaweed. How much of it, when you sink it, is actually sequestered? What's the market value if you, instead of sinking it, you bring it to shore and try to make something out of it? So we modeled this in a techno-economic way, again, varying these things over wide ranges just to see the sensitivities. And what we found out is that you could, for example, get seaweed. These are just the production costs. In the top panels, you're looking at sort of range from the minimum of our assumptions to the maximum of our assumptions. The median we came up with on the order of $800 for a dry weight ton of seaweed. So then if we looked at what's it good for, we considered 4 possibilities. You could sink it, and that would be the climate benefit of removing carbon from the atmosphere. Or you could use it for food for people, or for feed for livestock, which has been shown to help avoid methane emissions in ruminants, as I mentioned. Or you could make a biofuel out of it and try to replace fossil fuels. So all of these are theoretical possibilities. And it turns out in our model, when we look at really all the optimistic assumptions and the cheapest 1% of ocean areas, it seems like it might cost on the order of $600 for a ton of CO2 to be removed with this. So again, this is a pretty optimistic set of assumptions. And I don't know if you followed this, but $600 a ton is pretty pricey compared to things like direct air capture that people are talking about doing this industrially, which some people think could be done for $100 or $200 a ton. So it doesn't seem to me that it's necessarily going to compete in that marketplace. However, some of the costs here, like $130 per ton of CO2 equivalent for feed, or $30 a ton of CO2 equivalent for food, start to be pretty attractive. And the reason those are so much more attractive is that you're not just going to be offsetting carbon because of all the non-CO2 greenhouse gases that you might be able to avoid. You can actually get kind of a multiplier on your seaweed. So the only question there is, it's not obvious to me that we're going to be able to consume a lot of seaweed. So there may be a cap to that. Now, looking at the key sensitivities, this is, I'll breeze through. Things like line costs tend to be something that really matters. And this is sort of results that are useful if you're actually thinking about trying to grow seaweed. You want to understand, what are my major cost drivers? Similarly, that removal fraction in the middle is getting at, okay, I get a ton of seaweed, or rather a ton of carbon in my seaweed. How much of that is ultimately going to be removed from the atmosphere? Again, this might factor in some circulation patterns in the ocean, but a lot of it is just to do with what's happening downstream. Once you've taken nitrogen up in the seaweed, does that mean there's less phytoplankton somewhere else in the ocean? And so you're kind of fighting against nature, in which case you don't get the benefit that you'd expect. So all of these are sort of the important characteristics. And really, it was surprising to me, though, that it is possible to get to something like a gigaton of carbon removed with a relatively modest area of the ocean. So something I learned in the course of this project, it sounds silly, but the ocean is super big. So something even as small as 0.1% of the ocean is still like the size of Montana. So it's actually a pretty huge area to think about growing in industry. And so even though it looks possible to get to a gigaton removed at a price like $560 a ton, you'd have to do this over a huge area of the oceans. It's not obvious to me that we're going to do that. So we have built a pretty nifty tool too, if you wanted to check it out online, where you can go and look at our inputs, and you can toggle different parameters like the assumptions about line costs, and actually explore what happens to the costs of seaweed aquaculture in these different areas. So this is working with a terrific team at Carbon Plan. You can even zoom in on specific regions and adjust the size of that to focus in on different spots. So it is a pretty neat tool. And the takeaways here are that, it is possible, as I said, to get to pretty decent size carbon removals or offsetting greenhouse gases on the order of a gigaton, but it may be cost prohibitive if you're trying to do it for the sinking. And there's still a lot of uncertainties. Moreover, it would take up huge areas of the ocean that it's not obvious we're going to be able to do that quickly, or we would want to do it at all. And finally, I think it's probably in the near term, at least, better to try to use cultivated seaweed to offset conventional agricultural products than it is to just sink it. So just to try to tie all of these different studies up, you know, these top plots are showing you that more and more places around the world are setting goals of reaching net zero CO2 or net zero greenhouse gas emissions, including the darkest states here are ones that have rules in place to reach net zero, including New York. So I would sum up by saying, you know, we have a lot of exciting prospects for how to make progress toward these goals, but there's also still plenty of challenges to be studied, like how to really get rid of those land use emissions and whether we could really achieve carbon dioxide removal at large scales for an affordable price. And those are things that hopefully those of you in the room are going to be contributing to, as they're going to be interdisciplinary studies that are required. And I guess I'll just leave it at that and hopefully get some questions. Thank you.
Questions? Could you repeat them, Steve?
Sure.
So if chicken is such a small portion of like greenhouse gas emissions from the agricultural industry, how can we like so commonly hear that like for an individual a plant-based diet is more effective, and when you look up higher on the list you see something like cereal is far more impactful?
Yeah, well, part of it is that chicken doesn't represent nearly the number of calories globally that a cereal crop does. You know, something like half of our calories come from just maize and soybean and wheat. So chicken doesn't rate on that sort of table that I showed you because we're not producing nearly as much of it. And so its emissions are going to be less. But the point that I was trying to make is, and I'm sorry, I didn't repeat the question, why was chicken not a big deal when we so often hear that plant-based diets are the way to go. So anyhow, the point I was trying to make is that relative to beef, it's a pretty modest share of our current global emissions. That's not to say everyone should run out and start eating exclusively chicken. That would increase our emissions globally. It just means that maybe it's not as big of the total piece of the pie as you might think. Is there another?
This one here.
Yeah, sure.
Yeah. When you mentioned about like land use and like how using that is really important, were you doing like organic agriculture with all of this, because it's like it has a big problem. It's like yields are a big problem. Basically everything you talked about. So where do you see organic agriculture?
Yeah, so the question is about how organic agriculture fits into reducing our land use emissions. Yeah, I think, well, you saw that some of the most important improvements that we've seen in our land use emissions have resulted from increasing yields on our land. So I think the key would be, can we adopt more sustainable practices like organic agriculture without sacrificing those yields? Anything that we do that reduces yields risks having more land use change in order to compensate. So we either intensify or we extensify our agricultural system. And if we're expanding, we're actually going to be in a worse off place. So I'm certainly not opposed to it. I think it has a role to play in the solution for other sustainability challenges, as you mentioned. But we have to make sure that it doesn't lead to growth in the area of our agriculture.
So following up on that, often, from what I know, oftentimes when agriculture is intensified, that's not like sustainable over the long term. So how do you balance agricultural practices to have lower yield, like no-till, that's actually more sustainable over the long term. With, so I guess possibly less than over time. But in the short term.
Yeah, I mean, that gets to a question about sort of the time horizons of our decision making in general, which is a conundrum, I would say, in all environmental issues. I agree with you that being overly intensive about agriculture depletes the soil and can lead to degraded yields over the long haul. But it's something that I think we also have been successful in keeping yields pretty high in the US for a long time over a lot of our most productive farmland. So maybe there's a way to manage the present and the future without sacrificing one or the other. I didn't repeat the question, was about techniques that are intensive now and produce a lot of agricultural products, but over the long haul, maybe degrade them. And I don't have a great answer to that, but I think it's something to bear in mind. I agree with you.
Yeah, thank you so much. This is really impressive. Definitely good to check these ones out. I'm curious about the type of life cycle assessment methodological choices you're making. So are you doing consequential or attributional? And especially what's up with the decision of not assigning to or meet, which is the visibility.
Yeah, so it's mostly attributional, so it's all retrospective. We're not looking at sort of other counterfactuals. So this was about what sort of LCA methods. I'm doing a terrible job repeating the question, sorry. So it's all attributional, looking back at what actually happened and not using any kind of counterfactuals. The idea of the not assigning crops to the livestock sectors was mostly that we were adhering to this very production-based space, knowing that we were going to use that trade model in a subsequent paper to look at the consumption-based side of things. We did actually allocate the crops to livestock in some of the supplementary figures. And so if you're interested in that, you can go and find it. It is in the paper. It just wasn't in the main figures.
What does decoupling the economy from energy use?
I'm sorry, I missed that.
What is decoupling of the economy from energy use?
Okay, what is decoupling of the economy from energy use? The idea of decoupling is that we should be able to grow our economies without using more and more energy. So this can be because we're being more efficient, or we could have structural changes in our economic activities. Lawyers and doctors use a lot less energy than steel makers and cement kilns. So you can actually think about what kinds of activities you're doing in your economy, and hopefully you get to the point where you're able to prosper without using more and more energy.
So a few questions here from the webinar. So how does the variability of electricity demand change the viability of certain energy storage methods?
Yes, so I don't need to repeat this.
No,
one.
I think you.
I do?
No, you don't.
Okay.
I think everyone does.
Yeah, so as part of one of the studies that I showed where we looked at the different countries' variability of solar and wind, we did some cases where we looked at very different demands when we electrify transportation in particular, because the normal patterns of electricity demand are either more or less constant in the case of some industries, and then variable based on how much heating and cooling demands we have in our buildings. But when you start electrifying transportation, you get very different timing in that. And we expected that this would have a huge effect on how % of hours that you're able to meet demand. And we were actually pleasantly surprised that it had very little effect in most of the cases. So a lot of those results are robust to another system.
Another question, can you explain the pill factor trends that show agriculture emissions increasing rapidly and LUC emissions decreasing rapidly in North America?
Yeah, I'd have to look back at that figure, but agricultural emissions are typically tied to the conversation we've been having about how intensive your agriculture is. So if you're using a lot more fertilizer inputs, for example, or you're having more livestock and less crops, then it's going to increase the agricultural emissions disproportionately. But over time, we've actually decreased our land use change and had abandonment of land in the US. So that's going to decrease those land use change emissions. don't know if that completely answers the question. But
Yeah, thanks. And one more here. Potential additional uses that could help pay for production. This is in terms of seaweed.
okay.
Seaweed biochar to boost carbon content of depleted agricultural soils. Critical mineral extraction at some step of seaweed processing, or both, I guess. Can you comment on?
Oh, yeah. That's interesting. So I haven't necessarily thought about either of those, although I'm intrigued. I wouldn't mind knowing who asked the question.
Nate Chelsea.
Okay. Maybe I'll follow up. The other one that wasn't mentioned is something we have thought about is, there are places that are suffering from dead zones and hypoxia. And a lot of that's because of excess nutrient loading in the coastal oceans. So it makes a lot of sense to put your seaweed farm there, because then you're going to mitigate some of that nutrient pollution and get some value out of it. So you could maybe think of if there's a social cost of nitrogen, you could be gleaning that as well. So it's a good idea to think of some of these co-benefits. Maybe critical minerals are one that we should look into.
Any more? A few more here.
Yeah, so in your energy production section, you mentioned that to kind of like make up for this gap and the reliability, we're looking for something that has like a pretty low capital cost and maybe like a higher variable one. You mentioned natural gas as like an example of that. We want something that doesn't have CO2 emissions. Are there like alternatives that would fill that purpose, or is that something that's not really developed?
Yeah, so this is one of the conundrums, is that most of the non-emitting firm capacity come with relatively high capital costs, including if you're open to things like CCS. You add that to a natural gas fired power plant and you're already increasing the capital expenditures. So you're cutting into that. But other things like geothermal plants are probably going to be fairly capital intensive. Nuclear plants, very capital intensive. So things that we might think of as flexible still tend to come with high capital costs. So that's a challenge. I think that's where we went with the PGP idea of storing it as a gas with hydrogen, maybe one of the more attractive options if you don't have something like hydropower.
So, thanks a lot for this presentation. I was wondering, with the end product of that, you had briefly mentioned using that as food. Did you do any more research on the nutrient benefits or like?
Yeah, so when we're thinking about it at climate relevant scales, we were necessarily thinking it wasn't going to be seaweed salad people were eating for every meal, right? You'd have to find something that you could produce in bulk. And so the thing that we most carefully looked at was something like soy protein, where it gets used in a lot of places in processed foods. And soy, as you saw in the middle part of the talk, is a huge source of greenhouse gas emissions, especially where we're tearing down tropical forests to grow it. So that was the one we kind of focused on, that you could maybe get a lot of demand for the seaweed and thereby offset a good amount of the current emissions. It gets eaten. Seaweed is cultivated now, for all kinds of things, not just seaweed salad, but nori for sushi, and gets added to some other products as an emulsifier or in cosmetics. But it's such a small market that you couldn't get to billions of tons of carbon offset. So, yeah, right behind you.
Yeah, so I've heard like a little bit about a growing movement trying to move from consuming insects as like a source of protein. And I was wondering whether that's something you've ever heard about, and whether like it can be relevant on the scale, and if not, like why not?
Yeah, I actually had some students that did a project for a class not too long ago about eating crickets. Sorry, I'm not repeating these. This was about eating insects as a way to decrease emissions. And yeah, I haven't looked into it explicitly, but the term paper they wrote suggested that, there's very efficient in terms of the feed that you give them for the protein and nutrients you get out. Again, I think could you entice people to eat a lot of insects? And it could be a tough sell, at least in the near term, but maybe.
So during the presentation, you mentioned like something about sinking seaweed growing such vast amounts. I was wondering if you guys did research or like how that would affect the organisms that might live in the ocean. How would that affect that?
It's a question about the environmental risks of sinking a lot of seaweed. This is a hot topic right now, and no one really has a good idea. We don't think it'd be very good necessarily. It's mostly a question if you're sinking this in the abyssal ocean where you would maximize sequestration, is the ecosystem down there something that we should be that worried about or not? And so people have strong feelings about this. And I think there's some experiments that are going to try to look at this and actually like send down, AUVs and cameras to see what's happening with seaweed at the bottom. But, if you're sinking billions of tons of seaweed to the bottom of the ocean, it's going to have an effect. So we don't really know, but it's probably not good.
Right there. Yeah,
Sure.
Why exactly the seeds being investigated as a sort of viable? What are some benefits that were seen and were they investigated?
Yeah, so why was seaweed looked at to begin with? So it wasn't our idea to look at it. It's something that it's been out in the community as an idea. And one of the reasons is that seaweed, well, first of all, it's a way of getting carbon into biomass that doesn't take any added fertilizer, doesn't take any fresh water, doesn't take up any land. So all of those are attractive. It also grows extremely fast. And there's some kind of seaweed that can grow in almost any part of the ocean with a few exceptions. So for all those reasons, it's been thought, hey, if we could grow a lot of this, maybe it'd be a way of factoring in some carbon removal. And so there's people that have recently, there was a National Academy of Science report where they studied ocean carbon dioxide removals. And this was like one of 4 of the technologies they looked at. So we kind of wanted to see, well, if you really want to do this globally, what could you do? And what would it cost? Because no one had done that.
So you mentioned also using the seaweed as biofuel, and I mean, I have talked to some people who work with algae for a living who say that that's not necessarily feasible yet. So I was just wondering where you see we're at in the feasibility of actually using seaweed as biofuel.
Yeah, I mean, I've been persuaded by people that are in that domain that it is possible. Maybe it's not trivial yet, but it seems like a surmountable technological hurdle if we wanted to do it. What we found surprisingly, because I showed you early on, aviation is this thing we think is going to be really tough to decarbonize. So I was convinced early on that that was going to be the answer for seaweed. And I was a little surprised that it didn't win out. It turns out that at least right now, jet fuel from fossil fuels is remarkably cheap compared to what it would cost to make seaweed biofuels. And not only that, you're only going to be offsetting the CO2 that would have come from the fossil emissions, where if you can convince people to eat this and you're avoiding tearing down tropical forests, or you're avoiding a lot of fertilizer and nitrous oxide emissions, then you're going to have a lot more climate benefit. So those both ended up preferring food and feed. Maybe in the back, yeah. Sorry, I'll try to repeat it. Well, the main reason that any sort of nascent sustainable technology isn't viable is that fossil fuels are still so cheap and there's nothing driving the market in that direction. But all those policies that are in place that are going to be pushing people to find ways to get to net zero, I think are going to make it very real very soon. So, sorry, I still didn't repeat the questions. I'm terrible at this.
Any more questions? Great, so let's thank Stephen again.
Thank you.